Hello, my name is Richard Pham. This is Lab 6, Magnetic Braking with Faraday. Introduction. The purpose of this lab was to use the fundamental physics principles of Faraday's law, magnetic force, Newton's third law, and Ohm's law to use data collected from an experiment and compare it to a computational model. Materials used was aluminum foil wrap, ruler, magnet, and iPhone to record. Sneak peek of the results. All the laws were used together within a formula to calculate for the computational model. That time was 1.065 seconds. The experiment was average of 1.222 seconds, and the magnetic dipole moment used from lab 4 was 3.52 am squared. Physics ideas. So the main one being Faraday's law states that an induced EMF occurs when there's a change in magnetic flux over change in time. And then we use this equation of magnetic field calculated with the magnetic dipole moment calculated from lab 4 to then calculate the magnetic field, which is then used with this formula for magnetic force. Say here, current times length times magnetic field and sun theta. And then this is Ohm's law, which states that voltage equals to current times resistance, as we've seen before. And Newton's third law, which states that each force has equal and opposite reaction. Experimental conditions. Our initial conditions were to measure the length and width of the aluminum foil, drop the magnet, and time how long it takes to fall out the tube. System was aluminum foil and magnet, and the surroundings was air and other magnetic fields like metal from table or laptops and fans. Here's a video of us recording it. Okay, data. So this is the times for the 5 videos in seconds, and then I averaged it to get 1.222 seconds. Length was 0.4 centimeters. The width of the aluminum was 0.01 meters. The width of the inner radius was 0.015 meters, and the magnetic weight was 0.023 kilograms. Coding. So here is the first part, which is just to add in all our data from the lab, and also here to add in data from our lab. So this is mag of. Sorry, I just had to make sure I did the right new mag, and then this is our function here to create the magnetic field from our magnetic moment as well. This is just plugging in the values from the formula, and here it's also just plugging in values from the formula here with the respective variables. This formula here was given to us from the video. Yeah. And the coding. So this is just regular f-grav, nothing new here, and this is calculating the flux using our function that we created, and then this is the current using the EMF divided that by radius, and then this is equation for the magnetic force, as you said before. This is just current times the length and then magnitude of the B field in sun theta. Then this is all just kinematics right here. So the results were 1.065 seconds as time in tube. And this is our velocity, or this is the velocity versus time graph. Interpreting this simulation, so the intensity of the coloring on the tube indicates the magnitude of the current flowing through each ring. Red and blue indicate current flowing in opposite directions. Which color corresponds to clockwise current, and which is counterclockwise. So for lenses, all we know that red is counterclockwise and blue is clockwise. As the magnet falls, the magnetic field pointing down grows stronger. So by lens law, the current of the red has to be counterclockwise to counter the change of flux, and that's the opposite for the blue. That's why blue is clockwise. And what happens to the dynamics of the system when you flip the magnet around? Currents will swap direction as the magnetic field would swap directions. So how does the total time in tube and real world system compare to the computational system? So for the experiment model, I got a time of average of 1.222 seconds, while the computational model, I got 1.065 seconds. It's about a 14.74% difference between the experimental model, and it shows that there could have been, or it could have been more accurate if we considered other influences outside of the system, like external magnetic fields or air resistance. What does this shape of the velocity versus time graph tell you about the forces acting upon the bar magnet? So I can show you the graph again. So here at this part, these are when the forces are not equal to each other. And right here is when force of gravity is stronger because this is when it's growing in velocity. But here's when it reaches its terminal velocity where the forces are equal, and that causes there to be no change in velocity. And then here's when they're not equal again, which are at the ends of the tube. Assumptions and possible errors. So assumptions the magnet is assumed to be a perfect uniform magnetic dipole, and we're assuming that the magnet could wobble and rotate, but in the model we assume it's perfectly asymmetrical with the geometry of the tube. Also errors: incorrect reading of the time, incorrect measurements of magnetic dipole moment from lab 4, and magnetic field from the surroundings affecting the flux. So what if the resistivity of the conductor were reduced as close as possible to 0? So how this changed the dynamics of the falling magnet? So due to Ohm's law, the resistivity of the conductor is as close to 0 as possible. The current will grow stronger to match voltage. Stronger current means stronger magnetic force to oppose gravity, making the magnet fall much slower. And then this is actually causes the opposite. So holes or slots were cut into the tube. How would this affect the ring currents in your model? So since the currents need to form closed loops around the tube to create the rings, we modeled in the computer model, there would be less rings if we cut out holes in the tube, meaning there would be less current, which would cause the magnet to fall faster as there would be less magnetic force to counter the gravity. And that is my lab.